next topic that we want to talk about is physical vapor deposition. So as we mentioned before, you need to deposit different types of materials on the surface of your wafer, and we saw that in case of silicon dioxide we could actually consume some of the substrate and grow a film from the substrate, but in vast majority of the cases that's not possible. We have to use an external source of material and transfer some of that material onto the surface in a controlled way. Physical vapor deposition is one such technique. In PVD that we're going to talk about first, the process is physical, meaning that there's no chemical reaction happening between the material that we want to deposit onto the surface, the substrate itself, or any of the other agents in the environment. We'll talk about an alternative to this, which is called the chemical vapor deposition, in the next lecture video. All PVD processes are conducted under vacuum. So you usually have a vacuum level, we'll talk about the units, on the order of 1 milliliter or less for your, or 10 milliliter or less for your typical PVD processes. And because they are done at such levels of vacuum, they're line of sight processes, meaning that a particle that is moving from your source to your substrate, in most cases they travel in a straight line, or they travel in straight lines for fairly long distances. And because of that, you have shadowing issues, right? So if there's an obstacle, which could be another topography on the surface of your wafer, they can create a shadow of themselves onto the film that is getting deposited on the surface. We have two major techniques for PVD. One is evaporation, the other one is sputtering, and the third one that is called molecular beam epitaxy. It's basically a modified version of evaporation, a very, very slow and controlled way of doing evaporation. So we'll talk about the first two in this course as the main PVD techniques. The reason that we perform PVD under vacuum, I'd like you to think for a second or two about this. Let's think about evaporation. If I'm evaporating a material and want to have it deposited on my substrate to grow a film on my substrate, how would vacuum help me? And just think about it for a second, and then continue the lecture video. Well, it enables the vaporization of most materials. A lot of the materials that you have, a lot of solids basically, have very low vapor pressures. It's easier to vaporize them under vacuum. It also decreases the number of intermolecular interactions, right? So what this means is that you do not really have to worry about, your, let's say if you want to deposit a layer of aluminum on your substrate, if you do it at high pressures, by the time the aluminum leaves here and the time that it reaches the substrate over here, your particles, your aluminum particles can oxidize before they get to your substrate or form other forms of compounds. And actually, because of the randomness in the directions, they may not even end up on your substrate. They can go in all sorts of directions. And finally, you want to reduce the level of contaminations. If you are doing this evaporation in a vacuum, it means that you basically have removed all the other material in this chamber. So what happens is that when you evaporate your metal, hopefully nothing else is going to come and sit next to your metal particles on your substrate. So vacuum gives us all these benefits, and depending on how low we go in pressure, we give it names: low vacuum, high vacuum, ultra high vacuum. So low vacuum is about 1 milliliter range. torr is a common unit in microfabrication. It's equal, 1 torr is equal to 1 millimeter of mercury, or the other way to think about it is that 1 atmosphere is about 760 torrs. If you want to convert it to pascals, 1 torr is about 130 pascals. So low vacuum is about 1 millitorr, right? So it's about 1/1,000,000th of the atmospheric pressure. High vacuum is somewhere around 0.01 to 10 microtorr. So another 2-3 orders of magnitude of decrease in pressure. Basically 10 to the 8, 10 to the 9 times less pressure than atmospheric pressure. And ultra high vacuum, that is 10 to the -9 torr or less. We do not do any processing at ultra high vacuum levels other than MBE that was mentioned earlier. Typically our evaporation is done at high vacuum, under high vacuum, and sputtering, which we'll talk about in the coming slides, in low vacuum. Now, if you want to have these processes done under vacuum, you need a vacuum pump. There are many different ways of making pumps. So this is a rotary one. As you can see, it traps gas from the inlet and then expands it and then basically passes it out from an outlet to the outside. They're called mechanical pumps, roughing pumps. And this is one way of, one method of operation for these mechanical pumps. There are many different types, but this is probably a bit easier to understand. These pumps, these roughing pumps, can go from atmospheric pressure levels down to about 10 millitorr, maybe if you push it to about 1 millitorr levels. In most cases, you need to go below those ranges. A turbo pump is a type of pump you can use in those cases. In this case, you have a bunch of rotating blades that are spinning at very high speeds, 10,000, 12,000, 15,000 RPM. And the way they work is that they actually move at those kinds of pressures. You know, when you talk about 1 millitorr or 0.1 millitorr, there is really no continuous gas flow. So what is happening is that this pump is running, it is connected to a chamber, gas molecules in that kind of pressures are moving around, and then what happens is that from time to time some of these gas molecules come and hit the blades of this turbo pump. And then just through momentum transfer, the blade pushes that vacuum, that gas molecule down towards the blade set below it, and so on and so forth, and eventually to the bottom of this blade arrangement. At the bottom of this pump, there is a roughing pump. There is one of those vacuum pumps shown at the top that basically extracts the molecules that are gathered from the top and collected at the bottom of this vacuum pump, and then this just shoots them out. An older type of a high vacuum pump was a diffusion pump. In this case, what we had was an oil that would just go and grab onto the gas molecules in the environment. So what you would do is that you would just create, get down to about 10 millitorr levels or so. Then this coil would just spray down inside the pump, not inside the chamber, but inside the pump, would spray down. And then as it was coming down, it would just grab onto some of the gas molecules, bring them down to the bottom of the pump with itself. And then at the bottom of the pump, you had a heater where if you heated the oil, the gas that was absorbed to the inside the oil would just release, and it would be captured by a roughing pump and sent out to the exhaust. They are not used as much anymore because, well, in the early days, these were the pumps of choice because of their low cost and low maintenance needs. But you're putting this oil in the high vacuum environment, undesired definitely. Nowadays, turbo pumps are cheap enough that we use them in many situations. And a typical vacuum system, especially a high vacuum system, looks like this. You have a roughing pump, a vacuum pump that gets you down to about millitorr levels here, with a high vacuum pump over here. So initially what you do is that you open this roughing valve and pump down the chamber using your mechanical pump here. Once you get to about 10 millitorr range or so, you close the roughing valve, open the valve to the high vacuum pump, and the bottom of the vacuum pump is high vacuum pump is connected to that same mechanical pump, and you continue pumping the chamber down this route. With this technique, with these simple systems, you can get down to microtorr levels relatively easily. And by that, I mean with a system that costs you about 100K or so. So what happens when you drop down the pressure? Well, if we assume that the ideal gas law applies, we know that the PV is equal to nRT. You know, this is the ideal gas law. And once you drop the pressure for a given volume, volume in here is the chamber, the reaction chamber that you have. Once you drop the pressure, the number of gas molecules inside the environment will definitely go down, right? And the other thing that we will notice is that as you drop the number of molecules, gas molecules in this chamber, you reduce the chances of collision between them. So there is a parameter called mean free path. It's a statistical average of the distance that a gas molecule travels before it hits another gas molecule, right? So on average, how far should this gas molecule travel or would travel before it collides with another molecule? The average value for a large number of gas molecules is called mean free path. It is given by this expression here. Kb is the Boltzmann constant and T is temperature in Kelvin. And as you can see, the mean free path, well, is proportional to temperature, and, you know, Boltzmann constant, that's basically a constant. And assuming that the temperature is not a variable here, it depends on the cross-section of the gas molecule, which is obvious, right? The larger the gas molecule is, the higher is the chance of colliding with another one. And pressure, inversely proportional to pressure. So if you drop the pressure by a factor of 10, the mean free path becomes 10 times longer. Now, let's look at some numbers here. If you assume that you have a chamber that you're holding at room temperature, atmospheric pressure, the question is, what is the mean free path under these conditions? So the question is that if we assume we have nitrogen here with a cross-section of 0.43 nanometers squared, so sigma is 0.43 nanometers squared. Well, part A, how many atoms do I have in 1 cubic centimeter of nitrogen, which is, you know, air is mostly nitrogen. And B, how much is the mean free path for these molecules at atmospheric pressure? So from ideal gas law, I know that if you go up, N is equal to, from the ideal gas law at the top, PV over KBT. Okay? So at atmospheric pressure, this is 760 torrs times 133 pascals per torr. So this is the pressure at atmospheric pressure. The volume is 1 cubic centimeter, so that's 10 to the minus 6 meters squared, meters cubed. And Kb is the Boltzmann constant, 1.38 times 10 to the minus 23 joules per Kelvin, times the temperature. We are going to assume it is room temperature, so about 20 degrees Celsius, right? So 293 Kelvin or 300 Kelvin. And at the end of the story, once you put in all these numbers, it's going to be 2.5 times 10 to the 19 molecules. So that many molecules per cubic centimeter. Now, if you remember, we had 5 times 10 to the 22 atoms per cubic centimeter for silicon as a solid. For a gas, the concentration is about 2,000 times less. Right? So we have 10 to the 19 atoms instead of 10 to the 22. Now, I know that the next question was, what is the mean free path? So I use the equation that I have for mean free path, kBt divided by square root 2 of sigma p. P is in pascals, so I multiply again 760 torrs by 133 to figure that out. And if you plug in the numbers in here, lambda is going to be 66 nanometers. So on average, an a nitrogen molecule travels about 60 nanometers before it hits another gas molecule, another nitrogen molecule. Okay, so this was at atmospheric pressure. The second part of the question says, what happens at 10 to the minus 7 torrs? If we pump down the chamber to 10 to the minus 7 torrs, what is the number of atoms per cubic centimeter, and what is the mean free path? And you can go through the same calculation again as above, or you can just scale both of those numbers with pressure, right? So you go from 760 to 10 to the minus 7. Look at those numbers, and then what you will see that n is going to be 3.3 times 10 to the 9, and lambda is going to be, so this is per cubic centimeter, that many molecules per cubic centimeter, and lambda is 500 meters, right? So in the first case, well, first of all, you can see that we have far fewer molecules inside that chamber. If your chamber, the typical dimension is, let's say, about half a meter to a meter in diameter and about 1 or 1.5 meters tall, you all of a sudden will have 10 to the 10 times less atoms in that chamber. So that's okay. We can probably, it's probably not that easy to appreciate it, but it's a lot less. We can appreciate it better when you look at the mean free path issue, right? So previously, under atmospheric pressures, a gas molecule would travel only about 70 nanometers before it hits another one. Now it has to travel 500 meters on average before it hits another gas molecule. With a typical dimension of, let's say, about a meter or so for the chamber, this essentially means that most of your gas molecules, most of the vapors in these chambers, if you do it at 10 to the minus 7 torr, they just travel in straight lines. They are not deflected by any other collisions. No other collision will happen on their way from the source to the substrate. And this goes back to the issue that we mentioned earlier, that these are line-of-sight processes, right? So the particles go from the source to the substrate in a straight line if you do them at high vacuum, under high vacuum. Now, one point to remember is that we reduced the number of gas molecules in the environment by a factor of 10 to the 10. Same thing happens to your contaminants, right? So you had nitrogen and you looked at the number of nitrogen atoms and all that. But let's say for you, oxygen is a contaminant for your process. The number of oxygen molecules goes down by the same factor when you operate under such low pressures. So all those benefits that we mentioned earlier follow. Here is a graph for the vapor pressure of different solids. And you can see that, depending on, these are all metals, the vapor pressure at low temperatures is really small. So the y-axis here is logarithmic. And you can see that, at, let's say, below 200 degrees Celsius, the vapor pressure is on the order of 10 to the minus 50 torr, right? What is vapor pressure? Vapor pressure is the pressure at which, if you have an empty chamber, if you have an empty bottle, it's the pressure at which you have thermodynamic equilibrium between the material that leaves the solid and the material that goes back onto the solid, right? So the material that leaves and the material that is deposited. So what this tells you is that at low temperatures, 200 degrees, 300 degrees, the vapor pressure is so low that essentially none of this material is leaving the surface or getting deposited back on it. As you increase the temperature, however, things change. So at about 1,000 degrees Celsius, you can see that you actually are talking about, a vapor pressure on the order of microtorrs, right? So this is the level of vacuum that you can reach with many of the pumps nowadays. And if you raise the temperature of your, let's say, gold or aluminum substrate or target to those kinds of temperatures, few hundred degrees Celsius, all of a sudden you have a reasonable pressure, a reasonable amount of material leaving the surface of your source, and hopefully a good amount of that will end up on your substrate. So for PVD, for physical vapor deposition, we need vacuum, but we also need to increase the temperature so that we need vacuum so that things move in a straight line and we get rid of the contaminants and all that and avoid unwanted reactions. But we also need to raise the temperature, at least at the source side, so that you start to release enough of this material into the environment so that you get an appreciable deposition rate. So with those things in mind, here is a typical schematic for a evaporation chamber. Thermal evaporation is a process where you heat up your source, whatever metal, let's say, that you want to deposit on your substrate, aluminum, gold, titanium, even tungsten. You heat it up under vacuum and you put your substrate right above that source. There's usually a shutter between your source and the substrate so that you get more control over the start and stop time of the process. So you heat up the source, you start producing the vapors. Remember, it's under high vacuum, so everything is line of sight. As long as the shutter is here, the material will deposit onto your shutter. You open the shutter, you have the desired amount of material on your wafer, then you close the shutter and shut off the heat to your source. When you do the evaporation, you can figure out how much the flux of the material is from the equation shown here. We are not really going to get into too much detail here, but the important issue is that you get more material as you have higher and higher vapor pressure for your source. And to get higher vapor pressures, you need to increase the temperature. So how do we do the temperature? How do we do the heating? There are two approaches. The first one is Joule heating. So in many cases, what I want to deposit through physical vapor deposition is a layer of metal. And if it is a layer of metal, I can heat it up. Well, it's not really that practical to, let's say, heat up a wire of, let's say, gold if I want to vaporize gold. What I normally do is that I have a boat that is made of metal. I put my pieces of gold inside that boat, heat up the boat, and then hopefully heat it up to a high enough temperature that the gold will melt and vaporize. So that's Joule heating, but the problem here is that, first of all, it is wasteful. You have to consume a lot of power, and then some of the material that you evaporate will end up wetting the boat. So that is one challenge with it. The other problem is that you cannot heat up all materials to the amount you want. So for example, if you want to evaporate tungsten, you're in trouble because tungsten has a really high melting point. So the boat that you're using has to have even a higher melting point than tungsten, and there are not that many materials that can actually be used here. So an alternative technique is to use a E-beam heating. In E-beam heating, what you use is the beam of electrons. You just produce a beam of high energy electrons that you bend in an electrostatic, using electrostatic lenses, and guide it towards your target. The electron beam hits a portion or location on your target. Usually the spot size is on the order of 1 millimeter or so, or even smaller. And because it's a tiny amount of surface area and a lot of current through those electron beam, you basically heat up locally your source and you start to evaporate it locally here. Your boat and all those other things don't have to be there. The challenge here is that, once you hit a surface, a metal surface with high energy electrons, you're going to produce X-rays. So that's the only challenge. In some cases that could be a limitation, but other than that, E-beam heating is usually preferred over Joule heating if you can afford it. A Joule heating system is simple. You just crank current through your boat and then you evaporate everything. but with an e-beam evaporator, things are a little bit more complicated. The advantage is that you can basically evaporate everything. Now, with evaporation, the typical operating pressure is about microtorrs. 1 to 10 microtorr is typical, and therefore the mean free path is generally larger or longer than the dimensions of your chamber. So a couple of meters for your chamber, but mean free path that is tens of meters or more. And therefore, you may have shadowing effects. So if you have a source and you put your wafer at a distance from your source, known distance from your source, and there is a bit of a tilt to your wafer, then you are going to have, well, first of all, shadowing, and secondly, if you deposit at an angle, you're going to have a different thickness of the film on your wafer compared to when you put it straight in front of the beam of material. And you can go and, this section is explained in more detail in your textbook, but at the end of the story, the thickness of the film on your wafer will depend on the angle that you have between the beam of the material coming to your wafer, the tilt of the wafer, and maybe the local topography. And what you can choose, for example, in this case, is that if you're depositing directly onto this layer, you have the largest thickness here, but all these corners that are at an angle will have slightly less material on them. In this extreme that I'm depositing from the side, you get some material here and here, but this face doesn't even see the beam of material. So you actually get zero thickness here, and then you will see the bit of shadowing at the corner of this structure as well. So again, what this is intending to tell you is that depending on local topography, you may have a variation in film thickness, which is generally undesired, but in some situations you can actually take advantage of this situation and play with it to do some fabrication tricks. At the end of the story, if it is only local topography that is determining the variations in thickness, you can show that the relative thicknesses are proportional to the cosines of these angles with the normals to the wafer. Typical thermal evaporation systems, these are research grade systems, are like this. We have a bunch of them here at SFU within the engineering science clean room and also 4D labs. These are boats that I mentioned. So a typical boat looks like this, but if you have a material that doesn't melt easily, or you have a situation where the material wets the boat, you can see that whatever that was evaporated here has wetted the boat, right? It has started to creep around this boat when it melted. You can put them in crucibles. These crucibles are usually made of ceramics or maybe graphite that have really high melting points, and then heat it from outside. So you put a coil around it and still push a current through this coil to heat it up. And then one nice thing about evaporation is that you can have multiple sources for your evaporation. So in this case, you can see that this system allows for evaporating 4 different materials, one in each one of these crucibles here. And you can do them at the same time, or you can do this, then that, without breaking the vacuum. So you can deposit your chrome layer that you need for adhesion, and then gold layer that you need for, let's say, conduction, one after the other without breaking the vacuum, and therefore keeping everything clean. So that's the discussion for evaporation. The next physical vapor deposition technique that is very commonly used is known as sputtering. So in sputtering, what we do is that we take your source material, let's say aluminum or gold or anything that you want to deposit on the substrate. You bombard the surface of this source with high energy ions. And the hope is that when you do that, you detach some of the material from the surface of this source, and then hopefully they go and land onto your substrate. As you can see, you probably wouldn't expect a very dense film out of this process. In fact, PVD done through evaporation gives you higher quality films than this. But the good news here is that you don't really have to have high temperatures for your operation. On the other hand, because you have these high energy ions to impinge onto your substrate and remove material from the surface, the pressure cannot be that low, because low pressure means that your ions are also at a lower density. So typically sputtering is done at about millitorr, tens of millitorr at most. And a typical sputtering chamber looks like this. So I have my substrate here at the bottom, and a source material here is at the top, the target. And what I do is that I bring in argon into the chamber, ionize argon, shoot the ionized argon atoms towards the target material, put an electric field for that, right? So a large DC electric field is produced to guide the argon ions towards the source material. If I do it at high enough energy, I will cause the detachment of those particles from the source, and hopefully they will land on my substrate. Now, why argon? Well, think about it for a second. The answer is that because argon is an inert gas, it doesn't react with your source, and therefore when you bombard it with argon, you don't get a chemical reaction, everything remains physical. Another reason for using argon, let's say compared to neon or helium, is that it is a heavy ion, right? So it goes and hits the surface, it has a lot of momentum, and therefore the chances of getting some particles sputtered is higher. You can do it with xenon as well, but xenon is a heavier inert gas, but is more expensive and is more rare. So therefore most of the sputtering systems use argon. How do I ionize argon? Well, that is done through creating a plasma inside the vacuum chamber. So once you drop the pressure to about millitorr levels, you let some argon gas inside the chamber, and you produce a plasma using the electric field that is in there. And the outcome of a sputtering, as we described here, is a film that is more conformal than evaporation. The reason for that is that you're doing this at a higher pressure. So instead of 1 microtorr that you had for evaporation, you're doing it at 1 millitorr. Or instead of 10 microtorr, you're doing it at 10 millitorr. So the mean free path for these particles is about 1,000 times less. If it was 10 meters before, now it is 10 centimeters or a few centimeters for your sputtering system. And considering that the source and the target and the substrate are usually, tens of centimeters apart, few centimeters apart, when a particle leaves your source, it typically goes through a few collisions before it lands on your substrate. And because of that, there is some randomness to its orientation, and because of that, it covers the side walls of the structures as well as the bottom and flat surfaces. So you get a more conformal film, you get a more uniform film, which is beneficial in a lot of situations. The sputtering yield is the number of particles that you emit from the target per incidence of 1 argon ion. It's typically about 0.5 to 2.5. So you're not really creating too many of them that easily. Now, we mentioned plasma, so let's have a second and talk quickly about what a plasma is. A plasma is a state of matter where you have a lot of ions, a lot of free electrons, and a lot of atoms that are excited, basically meaning that the electrons have jumped to higher levels of energy, and you can either detach it from them or the electrons jump back. Now, how to produce a plasma? What we do is that we put a gas at the right pressure and apply a very large voltage across the gas using 2 electrodes. Once that happens, you always have a few free electrons in the environment. There's always some nomadic electrons that are in the environment. And the situation is that when you create this electric field here, you accelerate the electrons. The electrons go and collide with some of these gas atoms or molecules that you have in the environment. If the energy of the electrons is high enough, they can either, two things can happen. They can either excite, well, three things can happen. First thing is that nothing happens. The electron doesn't have enough energy to do anything to the gas atom. Second thing is that they can transfer some of their energy to the gas atom and then basically excite the atom so that one of the electrons inside the atom moves up to a higher energy level. And thirdly, they can actually have enough energy that one electron is removed from the atom. So the electron hits the atom, produces another electron and an ion. And now you have an ion. So the excited atoms, what happens to them is that after a while the electron goes back to its neutral state and releases the energy that it has, the extra energy that it has, as a photon. And that gives the plasma for any gas its distinctive color. So for example, for neon it is orange, for argon it is purple. But, so that part doesn't really help us much. But the ions that we have produced in this process, the gas ions that we have produced in this process, now they will see the same electric field that affected the electrons at the very beginning. And they are accelerated towards the substrate, towards the source under this field. And once they have enough energy, they can start to basically, due to the momentum transfer between this heavy ion and whatever that you have on the source, you are going to extract particles from your source. You have two flavors. The DC sputtering process is just what we described. You have a DC field to do so. The challenge here is that you can do this for conductive films. If you want to deposit aluminum or gold on your substrate, you can do that because the positive ions hit the source and start to remove the material from there. But if you want to sputter dielectrics, that's not going to work, because as you hit the source, you're going to charge it up. And over time, you are going to make it harder and harder for those ions to come and hit the source, so your sputtering yield will go down, and therefore eventually it can even stop altogether. So the alternative is AC sputtering. So what you do is that instead of having a DC field between the two electrodes, we make it an AC field. And in this case, what is going to happen over time is that, let's say if you have a dielectric at the bottom, you're going to negatively charge both electrodes, because what happens is that you oscillate the field between the two electrodes at such a high frequency that heavy, let's say, argon ions that you have here cannot respond to it, but electrons are quick. So electrons will go and hit the source or the substrate, and over time you have an accumulation of electrons on both of these, both the source and the substrate. But you choose the electrode areas so that in your substrate, you have a smaller electrode. And because it's a smaller electrode, you have more negative charges on it. So you will have a more negative charge, same number of electrons on both electrodes, but your substrate is the smaller electrode, and therefore the voltage on it is more negative. And when that happens, the positive ions that you have here, the argon ions, are going to respond to that DC field, and they're going to hit your target, your source. And by doing so, you remove material from the source, and then the material comes and sits on the substrate that is sitting on a larger electrode. Now, you can sputter both metals and dielectrics in this way. However, at the end of the story, you have a situation where the sputtering yield is not really that high. And what they do is that they add a magnetic field to the process where you put very strong magnets behind your source. And by doing so, the electrons that are produced in this environment, what happens to them is that instead of traveling in a straight line, they're going to take a spiral route. And because they're traveling now a longer distance, the chance of an electron hitting an argon atom and producing an ion is higher. So you can create more argon ions, and therefore you can create a higher density of ions and therefore a higher rate of sputtering. And then RF sputtering or AC sputtering is the one process that we just mentioned. There is an alternative to this process where instead of argon we can use another gas. So for example, you can sputter aluminum with nitrogen. In this case, what happens is that aluminum actually does react with nitrogen. So if you use nitrogen as your plasma gas, it goes and reacts with aluminum upon the sputtering process, and you can deposit aluminum nitrate. So this process is used if you want to create a compound and move from a purely physical process to somewhat a chemical process. Typical sputtering systems, again, look like this in a research grade facility. So in here, what you see is that this big tray down here is where you put the substrate. That's your electrode that has a much larger area. And then your sources are up here. So you can have 4 or 5 sources, deposit your electrode, put your substrate here, deposit whatever material that you want from this source, then rotate it, put it under this one, deposit your next material, and go back and forth. This is the characteristic glow of a argon plasma, and as you can see, you have a high intensity of plasma near the source over here. That's because this is a because of the magnets that you have behind the source. And over down here, I'm not sure how clear it is for you, but you can see the substrate sitting on a big tray. And you can do the co-sputtering and depositing alloys and all sorts of things using sputtering systems as well. So that's that for physical vapor deposition. As we said, this is a technique that you use to deposit materials other than oxides onto your substrate. Now the issue is that you're still limited to whatever your source has, right? So if you have an aluminum source, you're only able to sputter aluminum. If you have a gold piece, you only can evaporate gold. Your choices when you have a physical process are limited. You're not coming up with new materials. Whatever you start with will basically end up on your substrate, transfer from your source to your substrate. So will end up on your substrate. Now, the next discussion we're going to have is CVD, chemical vapor deposition, that you mix the right gases at the input of a system so that you get the desired film deposited onto your substrate. So that will be the discussion for the next lecture video.